Anyway, so we continue on from the next last lecture. So we go to the Van-Kampen theorem. So a good place to see this is of course the Hetch's book. So given a space X covered by some open sets AI such that any two or three of them meet at a path connected set, then pi1 of X sty. So sty arbitrary point is a quotient group of the free product. Okay. So these are just reviewing facts. So the corner is of course generated by so mapping it to this group. So for the same element in the in the intersection part, map to this part, and then that the other part, and then you put that into a corner. Okay. So for set complexes, this will give you all the you can this will enable you to compute the fundamental group. But for of course for higher homotopy group, it's not true. But for the cell complex, first fundamental group, this is true. And so if you have a space Y obtained from X by attaching some boundary to cell, then it's just going to be just pi star divided by this normal group. So this is normal group generated by the boundary curves of the attaching map. Sorry. So I should say this is generated by the normally generated group. So you should take all the conjugates and then consider that as the generator, right? Not just that as the generator, but all the conjugate of that element to be a generator of that group. So these are always a normally generated case. So when you talk about the corner, and then so for example, you can compute the fundamental group of bouquet of circles. So and the surfaces using this method. Okay, so that's so next we'll talk about the covering space. So given a manifold, a covering map is from another manifold is onto map such that for point M has a neighborhood O such that so you take the inverse image of this O, then for each component you can say it's a homeomorphism. Okay, so I'm just using the simplified version of covering space theory just for the manifold here. So for example, if you have a covering of circle, then you can take some circle that covers another circle some m number of times, and also the some real line can be covers a circle, and so another thing is you consider things like interior of disjoint smaller disks removed, and so you cut and remove the edges and then consider. So you have some disk and then you cut out some disk and then you cut a arc between them, and then you can make a copies of that, and then you sort of cross attach these things, and then you can make a covering. And then so for example, if you so for join of two circles, there are many sort of coverings. So for example, if you see Hatcher, then there are many things you can play around with. And the homotopy lifting. So if you have two homotopy maps to M, then you can if one lifts to M tilde, then the other one also lifts, and that kind of thing. So that's a very useful thing. And then so if you have a map from Y to M with Y0 going to X0 and F flips to Y to M tilde, so that F tilde Y on the F tilde Y0 go to X tilde 0, then this image of F star is inside the P star of the covering map. So this is a sort of a straightforward theorem, but the way we use it is that unless this F star, the image of F star doesn't lie in the image of P star, then you cannot live. Okay, so that's the only way you can lift. Okay, so that's gives you some obstruction of the whether you can lift or not. Okay, so that's how you use these theorems. And so next, so the covering space is related to the discrete group actions very much. So you have a automorphism group of a covering map. P m tilde to m is a group of homeomorphism, so that P circle F is F. Okay, so any each element is called the covering map. I should have said that better, but so also you can also call the uh, uh, called the deck transformation group. So and also pi 1 of x on m tilde x by the right on the right by path shifting. So whenever you have functions acting, then that's a left action. So you have some functions acting. So group of functions acting, then that's always a left action. So because you write f on the left, right? Functions are on the left. But this path lifting is on the right action. So how you do it is you take any point, and then you have another point on the cover of the inverse image, then you always can lift. Okay, and then this point is acted to this other point. Okay, so that gives you another action on the right, and so there's both left and right action, and these are somehow isomorphic up to some right left change, but we don't want to talk about that. So also covering is regular or normal if the covering map is a quotient map on the action of discrete group gamma acting properly discontinuously and freely. Okay, so you have some covering map, but this is really sort of a quotient map under the discrete group action. Then that's called the regular map. Okay, regular or normal. Okay, of course, in the book, we learned it differently. So if the fundamental group is normal, then the covering group action, there is this covering group action, which is transitive on the under the actions. But of course, you can so you can always turn this around to this fact, because this fact will tell you that it's transitive action. So that's just another way to write differently. And so, so the classifying the covering space of a fixed manifold is just the classifying by the fundamental, the subgroups, okay, up to conjugacy. But if you want to classify the covering space with the base point given on the cover, then it's just a set of subgroups, okay? So the conjugacy only comes when you doing the base point changes, okay? So the covering space can be ordered by subgroup inclusion relations if you do it like this. And if this subgroup is normal, then you can see that the corresponding cover is also regular, okay? Yeah, so that's a review. And of course, manifold has a universal cover, so we of course go to the orbifold with this fact, but often some topological space don't have any universal cover, but so you need some kind of conditions for this to happen. But manifold is really simple locally, so it has a universal cover. So so it exists covering which has a trivial fundamental group. So universal cover always covers any other cover of a given manifold. Okay, so of course this is kind of going to be generalized to orbifold case. Okay, so the sort of orbifold universal covering is something that covers every cover. Okay, and then So M tilde has a covering automorphism group gamma, isomorphic to pi 1 of M. So if it's a universal cover, then the covering automorphism group or the deck transformation group is isomorphic to pi 1 of M. And the manifold M is equal to M tilde mod gamma for its universal cover M tilde. And gamma is a subgroup of the deck transformation group. Okay. Okay, so I'm not, of course, proving that here, but just mentioning this. Okay, so as example, so you take M tilde to be R2 and T2 to be the torus. Then there is a map from sending P R2 to T2 by sending X, Y to equivalence class of X and equivalence class of Y, where just the equivalence class is just the mod 2 pi kind of relation. So what I'm saying is R2 you can do on R itself because X and Y are just R elements, so you can do 2 pi mod quotient. So I'm mentioning this here. Maybe the notation is so completely right, but so that's a universal cover because R2 has a trivial fundamental group and it's covering. You can verify that. And of course, let's say M is a cross surface of genus 2, then M tilde is, you can show is a manifold with the trivial fundamental group. So, and it's also two-dimensional. Then it's very easy to show it's just a disk. And then so the deck transformation group can be realized as a isometries of hyperbolic plane. So M tilde can be considered as a hyperbolic plane, and deck transformation can be realized as a isometries of hyperbolic plane. So, okay. So, for example, in torus, I have some graphics. So you have some group generated by two elements in this direction and this direction, and then if you take the quotient, that will give you some torus. So topologically, I mean, it doesn't matter which direction I take. Okay, it's always same, but of course, geometrically there are differences. Okay, so that's what we will be studying later. Okay, and then let's do the simplicial manifold. So the simplex is a convex hull of n+1 points. Is affine independent points. So by affine independent, I mean that you take a point and then any point, and then you take the difference vector. So affine space is set of it's just Rn, but you forgot the origin. So the difference is always a vector, but it's not. The origin is just not defined. Okay, so difference is going to be a vector. So any 2 points has a difference vector. So you take n+1 points, you take 1 point, and then you take the n difference vectors, and that's independent. Then you say it's affine independent. So in that case, convex hull of these n+1 points is homeomorphic to cell En, and that's an n simplex, and then the simplicial complex is a locally finite collection of simplices, so that any face of a simplex is a simplex in S, and the intersection of any two element of S is another element of S. So S is some sort of collection of simplices. So elements are the simplices, and then with these kind of properties. Okay, so this is a sort of definition of abstract simplex, simplicial complex. And then you take all the union of all the simplices inside. Then this can give you you can give a topology to it by some sort of weak topology, and this is called polyhedron in some books. Okay. And so once you have this simplicial complex, you can do barycentric subdivision. So you always take the so given a simplex, you take the mass center of the vertices. Okay, and then you do the right. So this is always done by induction. So start from 0 dimension, it doesn't change anything. 1 dimension, you add 1 point, so you get 2 more 1 simplices and 1 more 0 simplex. And then for two dimension, you add another point at the middle, and then you do all the joins here. Okay, and so on. So you keep doing it by induction, then that will give you a barycentric division. And that's a very important tool here in simplicial manifolds and in general simplicial complex theory. And the link of a simplex sigma is a simplicial complex made of simplices opposite of sigma in a simplex containing sigma. Okay, so that's a common definition of appearing in if you study simplicial complex. So you take a simplex and then you look at any simplex containing it, and then there is always a opposite simplex, okay, of that simplex inside the simplex, okay, and then you take a union of all those. You take all those as the element, and then that give you a simplicial complex. So that's called the link. Okay, so that's okay. So N-manifold can be constructed by gluing N simplices by some phase identification. So the idea is that if you just identify 2 top dimensional say N simplices by the faces, then that's going to be very close to a manifold. But the result is just N-dimensional triangulated space. But if you have link of any P simplex is homeomorphic to sphere of this dimension N minus P minus 1, then X is a manifold. Okay, so there is an algorithm to check some whether some finite simplex complex is a manifold by just doing the some sort of algorithm of checking the links. Okay, so for 3-dimensional manifold it's very easy, but for N-dimensional we might have to do all these kind of things. Then next, if X is a simplicial N manifold, then X is orientable if you can give an orientation on each simplex so that you can kind of extend over the common faces. Okay, so that's always doable. Okay, so then that's the orientation. And lastly, so I just do some thing with the surfaces. So surfaces are canonical construction is that you take a polygon with an even number of sides and you assign identification by alphabets. Okay, so these alphabets are so there are only 2. So for a label, there's only 2 edges with that label given. Okay, so that means that you can identify only edge with an edge and not with 3 edges or 4 edges. So then you don't have many surface anymore. So, and of course you can prove that, right? So that's of course in the Monkress some exercise. So as long as you give these labels, then you get a surface. Okay, right. So whatever label it is, it's just the rule is that you have only 2 for for a label you have only 2 edges. Okay, okay, and then so for example will be bygone. So bygone is like a triangle, but you can this edge is bent. Okay, and then you have A and A inverse. Okay, you can do that, and then you can always label these. Okay, maybe I should right. So you have this disk, and then it becomes A and then A inverse. So the other one is going the opposite direction. Then if you identify, then this is a sphere. Okay. But if you have A and A, so going in the same direction, A, then you get projective plane, right? And next we have a square, so we identify top with the bottom, and then left side with right side with left side, and with the same opposite orientation returns. And this is a two torus. Okay, so that's an example. So any closed surface can be represented in this manner, and so closed, I mean that it has to be compact here, of course. So if it's not compact, we can do it with infinitely many edges, of course. So you take 4 n-gon, and then you label edges A1, B1, A inverse, A1 inverse, B1 inverse, A2, B2, so inverse, and so on. And so result will be some sort of connected sub n tori, and it's orientable. Okay. So of course, connected sum construction is of course commutative and all that, up to of course homeomorphisms and so on. And then we have 2 n-gons, so the label is A1, A1, A2, A2, right. So the finally, I should say this is AN, not BN, okay. And then this is a connected sum of n torus. And projective plane is not orientable. And the genus is just this n, okay, so this is genus is n. So n is actually the number of, so for the orientable case is the number of torus needed to make this surface, and then so for non-orientable case, the number of projective plane needed for connecting this. So results are topological space and two-dimensional simplicial manifold. So in the two-dimensional and three-dimensional, there's really no difference between topological and simplicial, but in higher dimension, it's different. So we have some problem, and we can remove the interior of closed bore with surfaces, and the results are surfaces with boundary. So in this way, you can obtain all the compact surfaces. You take the closed surface, and then you remove interior of disjoint closed bores, and then these are surfaces of the boundary. Can obtain all of these. And of course, the fundamental group is of course given by this formula, because you start with one complex if you do this identification, and then you add just one cell to this, okay, which so from the labeling we gave already. And then this is going to be the presentation. So the what you caution out is a normal subgroup generated by this, and of course the Euler characteristic is given by the number of edges minus faces plus the vertices, and these are you can show it's a topological invariant, and so if you have a orientable compact surface of genus C with n boundary components, or n holes, which people say. So this is the Euler characteristic. Okay, so that's in fact you can any cross orientable surface contain 3G minus 3 disjoint simple closed curves, so that complement is a union of disjoint union of pair of pants. Okay, so pair of pants we often say that, but I think it's a Thurston's term, but it just means spheres with 3 holes removed. And it's why we think it's important is because it's elementary surface, in the sense that you cannot use any more essential curve to make it into another surface except the annulus in itself, right? Whatever essential curve it has, it doesn't become anything new or anything smaller. So it is really some sort of in two-dimensional manifold theory, at least this is some sort of a most elementary thing. Okay, so in the orbifold theory, we will have more of these things. Mm-hmm. Okay, so this is a graphics for how this octagon exists, and so this disk will cover this surface like this. So so if you look at these curves, and they of course there are much better graphics in the YouTube or something. So if you go to YouTube, there's something actually that shows you how this cut surface actually becomes this octagon. There are some graphics like that. And then and then of course, if you move this by isometry, which I didn't write, you can see that this is a universal cover. So the hyperbolic space will cover this, and these are sort of representation of a genus C surface, because so if you look at the genus C surface, it's just a torus added up horizontally, right? And so if you do it carefully, then actually there's a symmetry between top. You can reverse up and down, right? So if you just look at the upper part, then it looks like this, okay? And then lower part is the same. So in some sense, orbifold theory, you can think of it as a reflecting the surface. Okay, so if you cut this and then, but you remember how it was, the reflection of the lower side is just remembered by reflection, then this is enough to represent the genus C surface, right? And then orbifold theory sort of simplifies surface theory in this way. So because now you only have to deal with these hexagons. So if you look at this, these are all topological hexagons, not parapents. So parapents or the sphere of three holes is complicated, but hexagons are easier to understand. Okay, so this is one arc, one arc, one arc, one arc, one arc.